Yay! Let's talk about spin states and counterions, shall we? So, we have singlets, triplets, and multiplets. They're fun things, and they're determined by the pairing of the spin angular momentum of electrons. So when we have paired spins, the anti-parallel, it adds to 0, that angular momentum, and then we have a singlet. And then when they're unpaired, they add to something other than 0. We have a triplet or a multiplet. So here's a little graphic. Pay no attention to these. I don't like these unless you want me to rewrite them in something a little more intuitive. So here's our singlet. They add to 0, and there's only one way they can do that. For the triplet, they all add to 1 somehow. And there are 3 ways of doing that. Hence, triplet. And this is what you'll get in transition metals, because they like those better. They can get lower energy when we include the triplet multiplet states. Now, how do we get these in VASP? Caitlin already told us. In the in-car file, we set the I spin to 1 to exclude the spin polarization stuffs when we're working with the singlet species, and then to 2 to include the spin polarization when we want to include our transition metal stuffs. And then for counterions, they're kind of like salts, where you have a positive and then a negative ion. They counteract each other's charges and maintain neutrality. So those are fun. And this is the bad boy I'm working with. This little phenyl hydrogen crappy there.
Okay, that's thankful. So instead of going to technical details of practical computations, he gave us more theoretical background. And maybe Kelly wants to ask questions to this theoretical background.
Yeah, I do. I gotta think how to say it first.
Okay.
So.
Do you want me to switch to a different slide?
Well, it's about the pictures you have.
The pictures I have? Okay.
There's I feel foolish, but
Feel foolish?
there's no this is the correlation to like no, there is no correlation between what these singlet triplets are and what you see on NMR, or is it the exact same? Like when you see
It's
singlet.
different, because with NMR you're looking at nuclear spin. Right now we're talking about electron spin.
Okay, that's fine.
Owen?
I don't know if it's a question, but are the triplets like the p orbitals? I'm just trying to connect.
That's something I really hadn't considered. They don't have to be, because you can get the same thing in helium, which, although it does have p orbitals, they're not always occupied.
Can you hold for a second? And I will try to help Paul to answer Paulina's question. If you look through the printout and the previous talk by Caitlin, so it is what is in the printout is a previous version of her talk, which was also theoretical. And if you look on the slide 1, 2, 3, 4, 5, it does contain an answer to Paulina's question to Paul. I wouldn't say that it is very lay language, but it is formally correct. So it is what we were talking in our mornings. The overall wave function can be composed as a product of partial wave functions depending on a single quantum number. And we can look at an orbital as a product of a component that depends on position, like S, P, D, and a second component which depends on a spin. So spins and p orbitals are a little different. There is a connection in the word angular momentum? That would be my question to Paul. We will see how he would address it. But there is an angular momentum for orbital motion of electron, and it exactly deals with SPD electron. And there is a second component of angular momentum for electrons itself. Okay?
Question.
Joe?
Just a clarification, you said that those triplet states all add up to 1. Is that
They have angular spin momentum that is non-zero.
what's up with the middle one that
So
says
the
0?
middle one? Oh, this is the projection on the z component.
Okay.
If you add these two together, it will be 1 in the xy plane.
How would you categorize singlet versus triplet in terms of their geometry?
In terms of geometry, how do you mean by geometry?
So the singlet states, right, they point
Yeah.
in opposite directions. So would you say that they're parallel?
I would say they're anti-parallel.
What about the triplet states?
Triplets?
Are they orthogonal?
I don't know.
Do you know the answer and just trying to torture him, or you are really curious?
I'm curious, yeah.
Yes.
I don't know if they're truly orthogonal or if they're just not anti-parallel.
Oh, one doesn't need to establish connection between spins. One needs to add them according to vector addition. So if it will, total length of the total vector will be 1, and projection on the z direction will be 0 for the middle configuration.
But there's no parallel states in this. Can there be parallel vectors, or are they all orthogonal? That is sort of the heart of my question.
Okay.
Okay.
More questions? I have, but if you want, please go ahead. Okay, so you've mentioned angular momentum.
Yep.
Is everyone is happy with this word?
They're not.
So what's the difference between regular momentum and angular momentum?
What's the difference between regular momentum and angular momentum?
Yes.
Okay. So
Is it like momentum is a velocity, but we will look at it at an angle, and then it will become angular momentum.
okay. So here's regular momentum,
Okay.
and here's some angular momentum. Angular momentum, you're just rotating. It's the momentum of rotation.
But you draw a vector. Where does your vector point?
The vector is
Keep rotating and tell where the vector
okay,
is.
so if I rotate this way, my vector is going to go that way.
Okay. Okay.
And if it's going the other way, my vector will go this way.
Excellent explanation. Yes, you can stop rotating.
Yeah, I'm done. Is everyone happy with that? Yes, no, maybe so.
Okay, so let's keep asking you.
More questions? Who knows? I might spin in a circle.
Well, when you do practical side, we are telling alpha and beta component, or we tell spin up and spin down. And on your pictures, evidently, your spins are neither up or down. Maybe it relates to Joe's question. They are at angles.
Yeah.
What is the connection?
What's the connection?
Yes, why your background deals with vectors of angular momentum at some angles, and in our practical sessions we have only strictly up or strictly down. And when most of chemists do electronic structure, they draw little cells and put their arrow up, arrow down. You've never seen electronic structure with spin directed at 45 degrees. No? And Paul wants to sell it to us. Like, he spins at 45 degrees. What is the connection?
Okay. What is the connection between and, if I'm understanding your correct question? Okay. Okay. From what I understand of spin, it's a result of relativity of some sort. It comes out of relativity. And it's not really a true spinning of sorts, I think. But when we do put it in there, oh my gosh, where am I going with this?
You may try to explain it without relativity.
Okay. That may be more simple.
So suppose that your molecule is situated in an apparatus with a strong magnetic field.
Like an EPR.
Which implications will be exerted to your spins? Would they keep showing 45 degrees, or would they align along or against the magnetic field?
They would prefer to align with the magnetic field in
Okay.
some way, either with or against. Although I think with would be a lower energy than against.
Yes. And just for humans, it is much easier to think that somewhere there is a EPR machine that determines a direction, an axis. And we are looking only on projections on this axis.
Yep.
Then one can tell about either up or down. So he was thinking in the right direction, and it's an excellent presentation. In more advanced calculations that probably no one of us will need, but if one deals with tiny details of magnetization, there is a so-called non-collinear spin, DFT, that exactly allows spins to be at angles like 45 degrees or other degrees. But for basic applications, for basic properties of materials, a hypothesis that there is a selected axis works really well. More questions? Okay, that's enough. Let's thank Paul once again.